Hey everybody, we're going to look at something known as photoelectron spectroscopy. What this is a very complex piece of machinery used to determine how electrons are arranged in the atoms. Now we've talked about the models of the atom, the Dalton's model going into the plum pudding model. Then we ended up with Rutherford's model, and then we finally talked about the quantum mechanical model along with hydrogen model by Bohr. But anyway, what this does is this gives us some data to explain why we know or how we know that the electrons are in S's and P's and D's in those various energy levels and sublevels. I'm not going to get into the basic or the generals or the workings of how this machine is going to work. I'm not going to go into the diagrams and explain how this highly sophisticated machine works, because honestly I don't know, but that's okay, because what we're going to do is we're going to analyze the data, and that's really what we want to get. So I have this little video here that I got from the AP people that kind of does a good job of kind of explaining a little bit of what's happening in here and how we're getting this data without going into too much detail. So watch this video real quick, and then what I'll do is I'll come back and I'll show you some examples on how to interpret the data.
I have here a sample of several atoms of the same element, and if you watch what happens during the irradiation process, you can use this model to envision how the spectrum from PES is established. In order for a spectrum to be generated, though, you need a large sample of atoms so that electrons from all energy levels can be analyzed. So let's take a moment to look at the atomic level model. Pay careful attention to how electrons from the first energy level are different than electrons from the second energy level. So if we look at the irradiation, you can see it causes electrons to be ejected, and then the kinetic energy analyzer measures the energy of the electrons that pass through it. And so if we look at now a valence electron, you can see the valence electron has a different binding energy than the core electrons. So core electrons seem to build up the peak at about 6.26, and then that core electron amplifies that peak even further. If you look at this valence electron, you can see the peak at 0.52 binding energy seems to be amplified for the valence electrons. So one more core electron, you can see the binding energy of 6.26 megajoules per mole gets amplified. And so we see clearly for this atom, and we're obviously looking at lithium here, for this atom, the binding energy of the core electrons is significantly higher than the binding energy of the valence electrons. We're going to look at a different system now. We clearly have a different atom here. Think first what you would expect the spectrum for this atom to look like based on what you saw for lithium. So would you expect 2 peaks? Would you expect 1 peak? Would you expect 3? Would you expect them all to have the same energy, different energies? Just take a moment to think through it, and then I'll run the animation and we'll sort of see what happens as the spectrum builds up. So is there anything that looks different about this spectrum compared to what we saw last time with lithium? We still definitely see a splitting of energy between the first energy and the second energy level, but if you look to the right-hand side of the spectrum, we have an additional peak that we didn't see before. So clearly there is something different about boron than what we saw with lithium, and if we compare the spectrum side by side, you can see a couple of things. First of all, we still see one peak bigger than the other, so there's more electrons on that first energy level than there were in the valence shell or the outermost subshell for boron. But we also see a couple of things. There's something in boron about the second energy level that lithium didn't have. So now we have an experimental observation, some actual data that we can put in front of our students to start to build the idea that even within the second energy level, there are further refinements to our model, that we now need to introduce the idea of subshells. So you can use this data to introduce the idea of S, P, and D sublevels and the varying electron energy that is there. PES provides direct evidence that the Bohr model does not fully describe the electron shells, and our subshell model provides a further refinement to his first model presented.